All right, so to kick it off, pump pressures, right? Everybody's pumped on something. They understand that they got to determine what their pump pressure is going to be based on some different things. Can y'all tell me what are the four main factors for determining our pump pressures?
Intake pressure.
Yes and no, but I'm not going to include that in there.
Length of the leg.
Length.
Width.
So what does that go? So that is somewhat correct. That's going to be a factor into what you're figuring out from the length. What do you use the length to factor?
Distance.
Friction loss.
Friction loss, right? So let's say we'll put friction loss right here. And friction loss is determined by, Mr. Leiser? Say it again.
Length of the leg.
Length. And what else?
Width. Diameter.
Diameter of the hose. Very good. And I apologize for my handwriting. It's not the best. All right, what else?
GPM.
Nozzle.
Nozzle.
Type of nozzle.
So nozzle. So what are three nozzle types that we would have set pressures for? What's on the hand line? Fog?
Straight.
Okay, so hold on, slow down. So we got a fog. What's the set pressure for that? 100. What else do we have? Should be three.
80 and 50.
And what are those? So give me one of them.
80.
So the 80 is what?
Master string.
Master string. Very good. So master. And I'm going to say smooth bore. So we got 80 on that. And in the same regards, we got a smooth bore hand line, right? All right, so we got our nozzle, our friction loss, two more.
Elevation.
Elevation. So what is our consideration for elevation? Gravity, yes, that's correct. But what we have, again, I'm going to reference back to the fact that we don't use a lot of these calculations that you find in the book. We have predetermined pressures for almost everything, right? So what is our set pressure that we have determined as a department for elevation? Think about a high rise.
PSI per 10 feet.
5 psi per floor, 5 psi per 10 feet, both are applicable, right? So plus or minus 5. Why do I say minus?
Could be downhill.
Hey, I will remind you guys, this is going to go on the virtual desktop for people that want to watch this later. So when y'all are answering, speak loud because I want them to hear you. So this isn't just me talking. But that was correct. Say it again.
Below grade.
Below grade. So let me give a couple of scenarios. Obviously, we know about high rises. We're going to go 5 per floor or any multi-story building to overcome the gravity that Wadsworth, you talked about. What are some other areas within our city that we might have elevation issues that aren't just stories and buildings?
Parking garages.
Parking garages, yep. Where are you assigned at right now?
15s. Are you talking about Seneca Park?
Yeah, yeah. So like we get into that 4th district area and we got all the parks, right? You pull up to one specific house in that Cherokee Park area, you might have a hill that is the equivalent of a 3-story building, right? We have to consider fighting that gravity and getting that pressure that we want up there. So we would probably add 5, 10, 15 in that scenario, right? There's some buildings downtown. The Kentucky Convention Center, that's there at like 4th and Jefferson, right? Their floor levels are about 20 feet. They have a basement that goes about 20, 30 feet underground. That's an active area that they use. That's where we might get think about the -5, right? So if you're flowing to that basement, you're going to get increased pressure based on gravity assisting it. So is that a large enough amount that you're going to be worried about on the tip? No. But it's important to understand the theory behind that, right? All right, so we got nozzle, friction loss, elevation. What's the last one? Use the drawing.
Appliances.
Appliances. And what do we say is the set loss for appliance?
15.
15, correct. All right. So those are basically the four main categories, and we're going to go into those a little bit, and some of these slides that I'll show here in a second. We've talked about some of them. So obviously nozzle pressure. Y'all did mention we have the fog nozzle, smooth bores, and master streams that they're predetermined PSIs that we pump for them. Friction loss, we spoke about that. Friction loss is determined by the diameter of the hose, the length of the lay. And does everybody understand how that friction loss, why that takes place? You have a hose line with a rubber jacket and water moving through it, right? Friction is created as it's moving against that, reducing the amount of pressure that is able to build up. So why do we not consider friction loss in like standpipes or like the piping that goes to our deck guns?
Well, the deck gun itself would be
So what supplies the deck gun?
appliance.
Well, what supplies the deck gun? Does anybody know on one of our apparatus? What supplies it? 5-inch solid steel pipe, right? What is the standpipe generally made of in a high rise?
Steel.
Solid steel. Friction on that is so minimal that we don't really calculate it. So just understanding the difference, right? Again, stuff you may have heard before, not a big factor, but that's why we don't really consider any friction loss when we're pumping, 5 feet up to that deck gun. It's not needed. This equation here is out of the book. This is one of the equations that they go over again and again. It's just the equation for friction loss. So you have a friction loss coefficient, a flow rate, which we always assume is gallons per minute, and hose length. I would absolutely understand the equations in this chapter for the sergeant's test. Again, civil service is going to make these tests because we give them a book and anything in it's fair game. Some of those test questions might not be about anything we do as a department. It's important to understand how we determine friction loss and pump pressures, but I'm going to show you what we use. So for friction loss, the Louisville Fire Department has a standard, as you see up here on the board. I'm a little clicker. On the left there is 1 3/4 inch. So this this over here, this spreadsheet shows you 1 3/4 inch friction loss for 100 feet. Obviously our sections are 50 feet, so you would divide that number on the right by 2. Why is that number highlighted? That's what we assume based on manufacturer settings on the hose type we use. We assume that on our 1 3/4 inch lines, we're flowing 125 gallons per minute on average. So that's why we have a set standard, right? Everybody here has heard every 50 feet of 1 3/4 inch, we're considering 12 PSI friction loss, right? That number used to be 9 when I first got promoted. We also had a different manufacturer for hose that had a different flow rate. That's where that number comes from. Again, that equation before is how that is determined, but we know it, right? So we don't have to recalculate that every time. On the right here is our friction loss for 3-inch. Now, our friction loss on 3-inch is determined by gallons per minute, all right? So you have two ways of calculating that are highly acceptable. One is the traditional method, which is memorize those numbers. That works for some people, not me. That's not how I learned it. So you could say for 500 gallons, you're going to have 21 psi friction loss. And you can memorize that. I don't. I use a different method. I call it the finger method. Some books explain it like this. Some books have, there's probably, I think there's several methods in that book there. So let's say we're flowing 500 gallons per minute. I'll remove the 100. I say 5 times 5 is, you get 25. If I'm flowing 100 gallons per minute, 1 times 1 is 1. Now when I get in these 150s, the 250s, the 350s, I'll round up. Because the reality is you're not going to notice the difference of 5 to 7 psi on that tip. That will get you in a very close range. There's very little difference in 21 psi and 25 psi on that nozzle. Okay? So does that make sense to everybody? Finger method?
Yes, sir.
Or memorize. I've heard other methods. None of them make sense to me. Find one that works for you and understand how to get that number. So set loss for appliances. Up here I have 3 examples of appliances that we see quite often. There are many more. There's more than what we even carry on our apparatus. The takeaway from this is what we mentioned earlier. We have a set loss of 15 on any of these. So that first one there, just a gate valve, that's typically what you would see in a standpipe system, right? They'll be on the first floor. Inside the building, you'll have a Y or Siamese outside the building, and then every floor after that, where you hook up our high-rise kits, you'll have another one of these gate valves or OSMY valves. There's our Ys. Everybody's familiar with that, right? Come in many sizes: 3-inch to 1 3/4, 3-inch to 3-inch, 1 3/4 to 1 3/4, and so on. But the key takeaway here is we have a standard for what that loss is, 15. Elevation loss, we touched on that. It's not too difficult, 5 per floor, up or down, right? If you're pumping below grade, not going to make a big difference, but understand that you don't need as much pressure. You're going to gain 5 every 10 feet you go below grade. So calculating pump pressure. If you look at these 4 things, it can be quite simple. And we've touched on all of them. You got your nozzle pressure, your friction loss, which is on the 1 3/4 is pretty much predetermined. We just got to think about the length of the lay. On the 3-inch, we're going to be thinking about gallons per minute and the length of the lay. If we're using any appliances, we're going to add 15 per appliance. And then elevation. And those will give you your pump pressures that you need on all your individual gauges. Questions thus far? I'm going to skip over that one. Pump discharge pressure in pounds per square inch. That's another one of those formulas. I would know it. I'm not going to go into that too much. So what factors contribute to pressure loss? We've named some of them. Let's review. There's some things that contribute to friction loss that we haven't named, or to pressure loss. What are some things? Somebody.
Kinks in the hose.
Kinks in the hose, that's a big one. All right. What else? Busted hose, right? Kinks in the hose, doors shutting on the hose. Could be all kinds of things. What are we thinking as apparatus operators when we're having pressure issues? Like, what's our train of thought? Where do we start?
Square one.
Square one. I like that. There's not an absolute answer for that. When I was a sergeant, and if I came into a situation where I was having issues, I'll go from the source to the tip, right? So my train of thought was, all right, number one, do I got positive water? Is the hydrant operational? It is. Okay, from that point, where am I looking next? Supply line. Is it hard? Do I step on it and it feels stiff? Okay. If it does, I got water moving through it. Where's my next step? Somebody.
Intake open?
Is the intake open? Seen that happen a lot, right? It's an easy step to miss, especially if you've dropped the tank already and already given them water on one of the hand lines. That's the next step. All right, that's open. What are we looking at now?
Make sure the water's actually coming in.
Yeah, yeah. Do we need a prime? And we got the compound gauge, and we'll touch on the compound gauge later. So that looks good. Where am I going now? I got lines laid off. I'm gonna check my lines in the front yard, right? Do I have sloppy lays? Do I have kinks in my line that I can easily straighten and fix the problem? From that, do I have a punctured hose line, right? Is it, look for things that you can solve from the source to when they're going in the door. If you've checked all those things and you are absolutely certain that it's not on your end, that's when you need to start communicating to the IC, the incident command, that everything is good on your end, you've double checked it. They may have kinks inside. Maybe at that point, they're recommending that somebody go in and follow the line and fix it, like unkink it. Maybe it's kinked in a door, maybe it's around a corner and they're not getting enough pressure. But we have to be able to think, this whole idea of a sergeant is a guy that hears an address, drives really fast and tries to be the first one there and opens up a discharge and they're done. I think I've said this in these classes before, there's a lot of thinking going on with these positions, right? And there's a lot of troubleshooting and it's all in a very small amount of time. So to me, that's how I would navigate through that. Any other theories or ideas or things that have happened to any of y'all? Y'all like to talk, I'll tell you what.
No, sir.
On that note, since we're talking about you all not talking, understand when you become an apparatus operator, you have to be comfortable talking on that radio. I'm not saying that we need to have unnecessary communication, because we don't. We've had classes on that, limiting the amount of radio traffic that's not necessary. But sometimes it is, and sometimes you may need to communicate to the incident command. Sometimes you may see something and need to communicate to accountability. You have to be able to communicate to your hydrant position if they're not visible. So get comfortable with communicating, right? And if these are things that sound scary or like seem overwhelming, like thinking about problem solving, then you shouldn't take the test, okay? So if those things bother you, you shouldn't take the test. Simple as that. All right, I'll move on. I'll get off my soapbox. Multiple hose lines. So obviously with multiple hose lines off, you're going to be using several gauges, right? So we have the compound intake gauge, we have the discharge gauge, and all the individual gauges for each discharge that we have on that apparatus. So you're going to be managing gates, managing the pressure relief valve, volume versus pressure. So we'll go into a couple of those things individually. So everybody understand the idea is as you're throttling up to whatever the highest pressure you need, managing the gates and crimping them and locking them so you can get your highest pressure you need versus any intermediate pressures. Does that make sense? Okay. What's the purpose of the pressure relief valve? Somebody. Right. What's the purpose of the pressure relief valve?
Relieve the pressure so you're not giving too much at the end, somebody on a hand line or something like that.
Absolutely. So it's managing the overall pressure being discharged, mostly for the safety of the members on the nozzle, right? You can also think about our exposure lines. A lot of those things we can set up and leave, like the blitz, right? If we overloaded that thing with too much pressure, it's going to flip, and then it's got that mechanism inside, that safety, and it's going to turn off, right? So both, that's a good answer. So something I've heard that has been happening recently, or that the chief staff has seen a little bit of, with these pressure relief valves, something to keep in mind. You're supposed to be checking that every morning, right? Out of service criteria, correct?
Yes, sir.
Do we? We turn it on, turn it off, make sure it operates?
Yes, sir.
Okay. Can somebody explain to me, if it's not working, some simple things we can do to make sure, to try to get it working? Has anybody unscrewed it and taken it apart?
So you can check the spring inside of it and the filter inside to make sure.
So let's say we unscrew it. What do we see at that point? We usually have like a rod with a filter and a tip with a pinhole, and that's where the spring is, right?
Yes.
So what are things we can do? Vince, I heard you say something.
Clean that pinhole out.
Make sure that the pinhole is clear and clean of any debris. That filter, same thing, right? You can run water through it. A degreaser, make sure that it's clear. I've seen plenty of times, especially they'll get gunked up and a little rust in there, that if you take them out and clean them once a week, they operate a lot better. It's like everything else that we have on those pump panels. They're meant to be used and operated and lubricate themselves, right? So there are some things we can do to troubleshoot, not a lot, but that's about the extent of it. Oftentimes, once you do that, they'll work again. But something that has been going on is people will be coming in the morning. We've all heard the set it to 150, make sure it works, right, and leave it there. There's some different theories on that. Some people will say if your longest cross lay is 170 or 300 feet, that you should set it in that 170-ish range because that's what your pump pressure would be for that lay. Some people set it at 150. I think the key takeaway is, especially when we think about going from offensive to defensive operations, we take that apparatus that initially is pumping hand lines, right? And maybe 172 is our highest pump pressure. And then all of a sudden we're supplying tower 2 that requires 225 PSI. And guys are forgetting to turn that pressure relief valve off and understand and can't figure out why they're not able to get a good stream out of the tower. So me personally, I would come in every morning, make sure it operated, on, off, see if I could change the setting, and I left it off. That was how I did it. And if we anytime I pulled a hand line, I turned it on and set it to that one. That was my method. I'm not saying that needs to be yours, but I do think a consideration needs to be made that we understand transfer valves and pressure relief valves and when we use those. So we just made mention to when we're thinking about turning that pressure relief valve off. When do we go from pressure to volume, since we're talking about transfer valves as well?
Half the capacity of your pump.
Half the capacity of your pump. So Vince, not to keep picking on you, but since you're answering,
About 750,
so what is your pump capacity at Engine 6?
1500.
So about 750, you're going. So that 1500, what does that mean? Your pump capacity is 1500 at anybody? At draft. So what does that mean? What does that mean to you as a sergeant or an apparatus operator?
If you're in positive water, you're probably going to get a little bit more.
You're gonna get a lot more, right? All those ratings on our apparatus are at draft, meaning we're creating a vacuum and pulling water. You add positive water in that equation, you're gonna have a lot more capability. We're still gonna do like you said, Vince, and go at 750 and go to volume. And we're gonna throttle down when we do that, communicate that we're gonna do that, throttle down, switch to volume like you're supposed to. But just, I guess the point of all that is, understand your apparatus. Understand what hose lays that you have configured. Understand what appliances you have on track. If you have deck guns, booster lines, if you're articulating boom and you have the hydroforce, is that what it's called now? Since we're not using squirt. I mean, we have somebody assigned to one. Understand your apparatus, right? And as a sergeant, that's what I did. I knew exactly what I pumped to each one of my cross lays, my 3-inch lines in the back, my blitz, and then that removed the amount of calculations I needed to do on scene. So if I had to pull out a smoothbore hand line, I may have to think for a second because it wasn't a typical lay for me. But everything else, I knew. All right. So these are some of our set pressures. You'll see up there, the booster is 225. High rise, we want 500 gallons per minute at the fire floor. Our standpipes, we get that by doing 165 plus 5 psi plus the friction loss. Sprinklers, floors 1 through 3, we're going to pump at 150. 3 and above, we're going to go at 175. Do we want to go over those numbers?
No.
Why?
Bust the sprinkler head.
Rated.
Potential of busting the sprinkler heads. Then you went from having a protection system to a faucet, right? Makes sense? Fog nozzles, hand lines, master streams, we went over that already. Squirt base, 175. Ellis, is that still the same on the new one?
Thank you, sir.
It is, okay. Ladder pipe, 180. I did not put tower on there. What's that, 225?
Yes. Yes.
Y is 135. I've been hearing in other classes a different number. Have y'all heard a
I have
different?
as well, because the Y itself is an appliance.
Right.
So what number have you been hearing? I want to see if it's consistent with everybody else's.
15 is what I've heard.
To the Y? So anytime we pump to a Y, we're thinking and that's where we're going to this at this point. So in some of the other classes, I've been hearing that we pump 150s to the Y. And that's not wrong. I was always taught 135 to the Y. So that's why I drew this, because it was a topic of conversation in every class this week up until now. So let's say this is our configuration, right? We got a 3-inch line going to a Y, 1 3/4 line to a nozzle. Somebody tell me what the gallons per minute is here. 125. Is that part of what we're pumping? Not initially, because we're going 135 to the Y. I'm going to leave what we're actually adding up in red. We use that 125 to figure out our friction loss on the 3-inch, right? So based on our finger method before, 2 times 2 is 4. So our friction loss is 4. What are we pumping to the Y based on my calculation up there?
135.
135. What's our set loss for an appliance? What are those 4 added, or those 3 added up? That's how we get there. People may say 148, 150, 154, whatever. That's how they get to that number. Does that make sense? That's why we understand that on 3-inch, we need gallons per minute, and then everything else we have set numbers for. We have several types of gauges. Master intake or our compound gauge, and we'll go into a little more detail on that in a second. Our master discharge, which shows our total discharge pressures. Individual discharge for every discharge that we have on the apparatus. Oil pressure, tachometer, volume versus pressure, which we mentioned earlier. Pump temperature. Other than the pump temperature gauge, what's one way we can kind of monitor our pump temperature and make sure it's not getting too hot? Steamer cap, right? If it starts to get too hot, what are some ways we cool it off? I mean, obviously the point is you want to get water out of that tank that's heating, right? So you could flow more water. A lot of times that would happen when we're stagnant. We're not actually opening the nozzle. And we got pressure building up and creating friction and heat. We can do a couple other things. We can open up doors in the apparatus and get airflow in there.
Engine 9? Yes. There's a phone call for a representative from Engine 9.
They're outside.
Engine 9's outside?
Yes.
Okay, thank you.
So we can open up doors and get airflow moving through the apparatus. We can recirculate water. Does anybody know what that actually is? Like how you recirculate water, what you're using?
Tank fill and tank pump.
Yep. There you go, tank fill, tank pump, or put a booster line in it, but you gotta have that tank fill open. You start dropping water out of your overflow, right? What else can we do? Fans work. Cooler valve, yeah, that's gonna be something last resort, but that's the potential. Crack a discharge, right? Getting rid of water again, like your point earlier. I would recommend one that we typically wouldn't use on a structure fire, maybe like your trash line or something. But several methods, several ways to do it. Going into our compound intake gauge, this gauge measures our water pressure coming in. So that's measuring basically hydrant pressure, right? And how much water is coming into the pump. Obviously, different than the master discharge gauge, this has negative readings on it. So on the master discharge, it will only go to that, it'll only go to that 0, which my hands are shaky. On the intake, it goes to negative 30. Sometimes different manufacturers have different negative amounts, but that's for drafting purposes, right? Because creating a vacuum, seeing what kind of negative pressure we're building to create that vacuum. It also gives us an idea of our maximum pumping capacity. How might it do that? Any ideas? Okay. If not, let's say we have positive water. We open our intake and we got right off the bat, and we're in pumps, we have, let's say 200 PSI showing there, okay, at throttle. We open up a line and we see a 10% drop. So we go from 200 to 180. What does that tell us?
It still flow double what you're flowing.
You can probably get 3 more equal lines out of that. If you have a 20% drop, you can probably still get 2 more equal lines out of that. If you have a 30% drop, you can probably get 1 more line out of that. Equal flow, right? It gives us an idea of how much we still have left in reserves and how much, just what we have in reserves. And they're going into the next thing. Old school method that I used to see a lot, the sergeants in my house when I came on were Bruce Kelly and Jeff Whitus and guys that spent 17 and 15 years in one house as a sergeant. Big thing I always saw, and I think we've gotten away from it, is grease pencils, or I guess now you could use dry erase markers, but those guys would come in every morning and put a grease pencil in their pocket. I've seen Whitus and Bruce Kelly both do it. I'm sure your dad did it. They'd open that intake and they'd walk up there and take that grease pencil and mark it. They knew exactly what they had on that hydrant. They'd open up a line, they'd mark it. And they were monitoring their drops every time. So they could reasonably answer if a district chief or another captain came up and said, how many more lines can you give us? They knew. When's the last time any of you saw that? Never. It's probably a good habit to get back into. A lot of those things have been lost on us, but they were there for a reason, right? So that's one thing I stole from them. I always had that grease pencil. Didn't use it every day, but if I got in the situation, I always felt like I had a pretty good idea how many more lines I could give. All right? Have we all heard on the compound intake gauge, don't go below 20?
Yes, sir. Yes, sir.
I'm going to contradict a lot of people, but why is that?
You're trying to prevent cavitation.
Cavitation of your pumps? Is that what everybody's heard?
Yes.
I've heard that. I'm not saying it's wrong. I think based off the things I've read and people I've talked to even within our own department, that's not the biggest fear of going below 20. You'd have to get really close to that 0 number, and we're never going to get in the negative unless we're drafting, before you start cavitating the pump.
Is that number for the master pipes or whatever under the ground, that way they don't blow up?
Let's get to that. This is the big fear to me. So, yes, and I think we've had this conversation before, maybe. Atmospheric pressure, everybody understand what that is? That is the atmosphere constantly putting pressure on the surface of the earth, right? That is measured at 14.7 psi. So that means everything, including us, constantly has 14.7 pounds per square inch pushing on us. Theory is, and Mr. Goodman can probably correct me because he's a plumber. He knows a lot about this stuff. When you have water moving through those pipes or even static in that pipe, they have an amount of pressure built up. It's like a static pressure, right? And that pressure is always pushing out on the walls of those pipes, those hydrants, or 5-inch or hand lines. That's why they get hard. When those numbers start to drop below 20, that is showing you the amount of pressure left in those lines all the way back to the water mains and feeders. Now, I'm not saying this will happen because our construction materials are pretty good, but in theory, if the pressure and the water amount flowing through it drops below 20 or below that 14.7, you have a potential for the water main collapsing on itself because the atmospheric pressure pushing on it is greater than the force pushing out. So why is that a problem? Obvious reasons. You have that hydrant pipe or that piping for the hydrant or that feeder collapse on itself. You're switching back to tank water and you got 500 gallons to work with. You're very limited, and after that, you're basically an expensive service truck because you have no other capabilities. That's scenario number one. You've removed yourself from the game. Scenario number two is outside of that feeder, let's say the main collapses. You could potentially have just killed that entire grid, meaning every hydrant in the immediate area is no longer going to provide us with the water flow or the pressure that we need. So at that point, what are we doing?
Find a hydrant and relay.
Yeah, we're going to be finding hydrants and relaying. It's probably going to be from a good distance. So that would also mean incident command is going to be calling for other companies. So let's say he calls to dispatch, to communications. It's going to take them a couple minutes to dispatch, right? And then probably on average, since it's not their first alarm, we're going to say 6 minutes to get there. Then 5 minutes to get set up, 5 hydrants, lay 5-inch supply lines everywhere. You're talking 12, 14 minutes at best. What do we say about fire growth? Every minute, what does it do in a structure fire? Doubles. And we're talking about 15 minutes down the road. Catastrophic failure, right? That's my point. I'm not saying the cavitating the pumps is wrong. This should be the number one concern. This is why we don't go below 20. Now, if you're ordered by incident command to go below 20, I'll leave that between you and incident command. I would have a comfort level with telling anybody why I'm not going below 20. Fair enough? Does everybody understand that theory? Did I mess that up? Pretty spot on? You're the expert there. Net discharge or net pump discharge pressure. It's the pressure. I'm not going into that. You can read that in the book. It's again something you may need for the test. That's again going back to understand your pump's capacities, understand your apparatus, understand the tools you're working with, right? We've said it a bunch during this class. Knowing your apparatus is going to be the key. Knowing your first alarm, knowing what resources you have, that's going to make you a successful apparatus operator. Questions so far? Y'all are quiet. All right, that is the end of my presentation. I would like to show you all one more thing. So I'm going to minimize this. So y'all remember those like spreadsheets that you saw throughout the presentation? If interested, I can send you that, and it's all in one page. Me personally, when I was a sergeant, I made this. It has everything that we kind of went over today in a one-page document, from 1 3/4 to 3-inch to our set pressure losses, to the formulas. They're right there, terminology. And this, when I printed this out, it fit easily in my sergeant compartment, and I taped it on. That way at 3 o'clock in the morning, if I was having foggy or had a brain fart, I had a reference, right? Just like we have the SOPs as a reference when we're in the house, I kept this on the apparatus. Probably don't need it, good to have. Anybody, y'all want me to send this to y'all? All right, I'll send it to everybody that was in here. I'll send an email out. But again, you know, as things change and we change manufacturers, you might have to go in and change some of these numbers add things, change things, but at least we start having a consistent resource out there for people to use. All right, guys.